Hi, good morning, everyone, and welcome to our next presentation in our Your Universe series. We're going to be talking all about Pluto today, and we have a whole panel to do this. We have faculty and staff from Ball State's Department of Physics and Astronomy, which we are a part of as the planetarium on campus. And I'm Dana Thompson, the director of the planetarium. It is the largest planetarium in Indiana that we have here at Ball State University. It's a 16-meter dome, so about 52.5 feet across, and we have amazing technology inside that dome that projects onto it and recreates the sky. And we wish that we could be having this presentation with you all inside the dome, but unfortunately we're not able to. So we're bringing you the next best thing, a presentation here live on Facebook with faculty and staff from the Department of Physics and Astronomy. Well, again, I'm Dana Thompson, the director of the planetarium, and welcome everyone. We're going to be talking a lot about Pluto today and answering all of your questions about Pluto. So if you have any questions during this presentation, go ahead and put them in the chat and we'll get them answered here. And if you have any comments or any answers to our questions, you can put them in the chat here too. So hopefully we can get a lot of engagement from people watching today and really have a great discussion about Pluto, dwarf planets, the Kuiper belt, what even that is, and more in our solar system. To help us out today, we have quite a few people. So let me go ahead and introduce them. Let's do it one at a time. We'll have Rachel, our planetarium show specialist, introduce themselves here.
Hello, I'm Rachel Williamson. I'm the new planetarium show specialist here at Ball State. And before this, I taught science in the classroom for 13.5 years.
Great. And you have probably heard Rachel's name before, but I don't think this is the first time she's making her appearance on Facebook. So welcome, Rachel, to the video side of things. But Rachel usually comments in the chat for our live presentations, giving you that information about those extra bits of information about the object that we're exploring that week. We also have Todd Vaccaro from the Department of Physics and Astronomy here. So Todd, you can go ahead and introduce yourself.
Hi, how you doing?
So Todd's spoken with us before. He's talked with us before about the Radio Jove project at Ball State and how they use it to maybe explore Jupiter and other radio signals in our solar system. So good to have you,
beyond.
Todd. And beyond, yes. And then we also have John Millis, our new department chair for physics and astronomy. John, go ahead and introduce yourself.
Hello, everyone. I am John, and as Dana said, I am a professor of physics and chair of the Department of Physics and Astronomy here at Ball State. And my research background is in what's called astroparticle physics or high-energy astrophysics. And I typically study black holes and neutron stars using gamma ray telescopes.
Great. Well, thank you all for participating today in our panel. If anyone's watching and has any questions about Pluto, put them in the chat whenever you have one. But we already have some questions that we gathered from the community and then also other planetarians. So people who work in planetariums have said, given us their most popular questions that they get about Pluto and dwarf planets and the Kuiper belt and so on. So we have a lot of questions to go through today. Let's go ahead and get started with them. But and to do that, we're going to start off with the most basic questions that were asked. And to do this, or to answer it, I'm going to share my screen and give you a tour of the solar system, the basics of our solar system. So we all are kind of at the same starting point when we are having these conversations about Pluto, the Kuiper belt, and beyond. All right. So here is a basic view of our solar system, and it's pretty much to scale. So the objects here, like the sun in the very center of our solar system, is about this right size compared to the planets here, as well as these imaginary lines that are not really out in space, but we can put them up in the simulation to show the orbits of the planets. So the orbits of the planets here are about to scale too. It's about the right size compared to one another. So we have in our solar system, of course, the sun at the center, And the sun is the only star in our solar system. All the other stars that you're seeing here are beyond our solar system, really far away, outside of our solar system in our galaxy. So our solar system is the sun and everything that goes around it that's gravitationally bound to the sun. So that includes things like the planets here. We have 8 planets in our solar system. We have Mercury, Venus, Earth, Mars. We have Jupiter up here, Saturn, Uranus, and Neptune too. So let's take a little bit of a fly through around our solar system and see what else is there. Because we have more than just the planets in our solar system, right? We have between Mars and Jupiter, we made a whole bunch of these objects really big so you can see them better. So now it's not to scale. And those are our asteroids. We have about 2 million asteroids in our solar system. Most of them lie in this area here between Mars and Jupiter. And there's other objects in our solar system too. You probably heard a lot in the news lately about a comet that has been making its appearance in the early morning sky. And that comet came from a really far distance. It took thousands of years to get close enough for us to see it in our sky. But it came from a region of the solar system that we call the Oort cloud. But there's something else here too. And if you look closely beyond Uranus and Neptune, there's some specks here. Maybe I can zoom in to see them better here. But they're not actually stars. It's another region of our solar system, a belt around or beyond Neptune called the Kuiper belt. It's like Viper, but with a K. So it's the Kuiper belt. And that's where Pluto is and other objects like Pluto called dwarf planets. And we'll explain what that really means later. But let's see what those dwarf planets look like a little bit as far as their orbits anyway. So there's actually a dwarf planet where the asteroid belt was. Let's pause it here. So it's a dwarf planet called Ceres, and we'll talk more about it later. But in between Mars and Jupiter, remember there's a whole bunch of asteroids there. Well, there's an orbit for this object called a dwarf planet, Ceres. And then we have other ones too. They're all in green here. And it's going a little jumpy, so I'm going to forward and go fast forward a little bit. Here we go. So in green, we have the orbits of these dwarf planets. So there's Pluto here. And then there's other ones that we'll discuss more later on in the panel. But our solar system is more than just the sun and the planets. It's more than just these dwarf planets here. There's a lot to it. So let's go ahead and learn more about Pluto and other dwarf planets. And we're going to start with the question, how did Pluto get its name? And I think, Todd, you said you were going to answer this one.
Yeah, happy to. I'm going to go ahead and share my screen. I've got just a couple slides that kind of address the naming issue here. Screen 2. Should share. Okay, so kind of in line with a little bit of history here about how things get their names in general, especially with respect to planets. Uranus would be the first telescopically observed or discovered planet in 1781. As far as a name goes, it went through some possible versions. When William Herschel originally discovered it in 1781, he kind of wanted to name it after King George at the time, which would have been kind of awkward. Because when you consider all the different names of the planets, they were all historically named after Roman and Greek gods. And so after that, we had the discovery of Ceres. So you just mentioned that. And so we now know that that is a dwarf planet. But when it was first discovered in 1801, it was first thought to be a comet. And then when they realized it had a stable orbit and never formed a tail or anything, it was not a comet at all. Others started to realize that it was most likely a planet. There are other reasons why that particular object was thought to be a planet. At the time, there was a sort of a mathematical formula that sort of predicted where all the planets would be, and it happened to be that this area was an area that should have planets. And so they thought, aha, this mathematical prediction is correct, so it must be a planet. But then when they started finding more and more of them within just a few years of this initial discovery, William Herschel himself actually said, you know, I think we should probably call these things asteroids. They're not really significant planets. And so the name sort of stuck from that point on. So we have a case in history where something that was originally thought to be a planet was turned into something less significant. And so we now know that there are just lots and lots of these objects out in that area between Mars and Jupiter. Neptune would be another discovery, although that one was not accidentally discovered visually by a telescopic observation. It was predicted mathematically because they thought that there was perturbations, which is gravitational effects due to the nearby planet Uranus. And they did go out and actually find it from just that mathematical prediction. But then getting to Pluto, planet X was a similar situation where they thought that they had some perturbations on Uranus, and Percival Lowell in the early part of the 20th century started a campaign to go out and look for this ninth planet that they basically called Planet X. And so it would be some years later when Clyde Tombaugh discovered Pluto in 1930 that Planet X had been found. Now, Planet X is not a formal name, and so that had to get a better name than that. And so they would ask for something to come up for it. And while they were waiting, this 11-year-old girl in England, Venetia Burney, actually was sitting at the table with her grandfather, who I believe worked for a library at the time in England. And she saw the article, or they were talking about this article about the discovery of Planet X. And they said, well, what should we name it? Or what should it be named? And she said, well, all the other planets have these Roman gods names. And so she had been studying that stuff in school. And she said, well, Pluto hasn't been used. That sounds like a reasonable one to pick after the others. And so her grandfather submitted her idea, and word got around to the observatory in the United States, and it got out that that was pretty much the best idea they had heard. And so it officially ended up being the name of Planet X. And so on this slide here, I just have a few images of what Pluto depicted on a stamp years ago, showing Pluto with his guard dogs, multi-headed guard dog Cerberus or Kerberos, and holding his staff, which is sort of like a bident, you know, sort of instead of a three-prong trident, it's just a two-prong sort of staff. And the symbol that got officially designated for Pluto, the sort of hybrid P and L. At first, it looks like, oh, that's just the first two letters of Pluto. And that's true, but it also was sort of a nod to Percival Lowell, the initials of the person who started the search for Pluto. And so there's the pretty rich history of where Pluto got its name.
That's really interesting, Todd. So Pluto did not get named after the Disney character, right?
No. So yeah, I've got a slide for that too, which is kind of interesting you bring that up. The dog, if you go back in history and look at it, the dog came out with its name being Pluto about within a year of the discovery of the planet at the time, Pluto. And it's an interesting history there too, because Disney had this dog show up in several cartoons with different names, and then it finally got its identity shortly after the planet was discovered. And Walt Disney has denied that that was a ploy to, feed off of that particular namesake. But along with Pluto itself, I thought this was kind of interesting. I'll just mention it because it's on this slide. There was this product years ago called Pluto water. And Pluto water is a mineral water that was actually sourced out of French Lick Springs in Indiana. So right here in Indiana. And it had been used probably even before the turn of the century. So up until about 1971, People used it as a laxative, apparently, and it was a product that was sold up until that time, and then they realized that it had a significant amount of lithium in it, which is a controlled substance today. So you don't see this on the shelves anymore.
That's great. All right, so let's go ahead and move on to the next question. We'll hear from Todd again, but I think we're going to hear from John next. The question is, what makes a planet, and what is a dwarf planet? Is there like a size limit to either of these things? John, can you help us figure that out?
Yeah, that's a great question. And the main thing is that planets and dwarf planets are actually very similar in a lot of ways. And in fact, there's three characteristics that define what a planet or dwarf planet is. The first one is that the object must be large enough, have enough gravitational energy to form itself into a spherical shape or similar to a spherical shape. And so, objects like Mercury and Earth and the Moon and Pluto all fit into that kind of category. The second characteristic is that the object must orbit the sun. So this is where you get into why an object like Earth is considered a planet, but our moon is not, because the moon orbits the Earth, not the sun. So that disqualifies moons from being considered planets. The third one is where we begin to differentiate between a planet and a dwarf planet. And the way that this characteristic is defined is that the object must have cleared its orbit and be the dominant gravitational force within its orbit. Now, that sounds a little nebulous and sort of difficult to understand, but the basic idea is that when the solar system was forming, when the planets and dwarf planets and everything were forming, there was a lot of stuff and debris around. The planets are those objects whose gravitational presence was significant enough to clear out any of the debris that was in the area. Now, of course, there's still little bits and pieces and maybe some small asteroids or something here and there. You could look at Jupiter as an example of that. But being the dominant gravitational force and clearing the vast amount of debris from the orbit is really what separates a planet from a different type of object. Some of the smaller gravitational bodies in our solar system that are large enough to be in a spherical shape and that orbit the sun, but they're too small to meet that third criteria. So objects like Pluto or Ceres in the asteroid belt do not have enough gravitational presence in order to clear the other stuff out of the way. And that is why they fail to be classified as planets, but instead as dwarf planets. In terms of having a mathematical limit for where that happens, scientists have made some attempts to come up with some measurements, some metrics that we could apply to planet and dwarf planet candidates in order to separate them. There's no consensus on what the best metric is, but if you look at the data, you can certainly see a separation mathematically from the objects in our solar system that are classified as planets to those classified as dwarf planets. There's certainly a very big difference mathematically to those objects. But where that line is and where we define that point hasn't really been determined yet.
Yeah, I think that's interesting. And sharing back my screen, when I showed the asteroid belt in between Mars and Jupiter, hopefully you can see here, but Mars does have a lot of little dots by it. Those are representing asteroids, and so does even our Earth and even Venus, and Jupiter has some near it too. So it's not really clear how much they have to actually clear out their orbits in some of these definitions, but scientists do their best, I think, to try to figure out, where certain objects fit into categories when they can.
And can you see the Trojans with Jupiter on this anywhere?
Yeah, so it's a little harder to see too. Let me try to go slow here, but there's definitely some clumps of asteroids in what are called the Lagrangian points of Jupiter. So kind of where the gravity is nice and objects can hang out pretty comfortably here gravitationally anyway. And those are the Trojan asteroids. So there's definitely a lot of debris in our solar system, not it's not always, space isn't always empty like some people think, right?
Yeah. And that brings up a really good point, Dana, that particular characteristic, it's one that's been debated and discussed even among scientists, and I think is what brings a lot of, I don't want to say controversy, but a lot of sort of discussion and debate about the classification, because it seems like it's not very specific in the way that it's applied. But the understanding that scientists have is really that in order to be considered a planet, it must be the dominant gravitational force. And the way we kind of talk about that again is this idea that it has to clear its orbit. But as it's kind of worked so far, it's been sort of black and white. And again, there's been attempts to be more specific about it and actually create a mathematical metric by which we can measure. And attempts that try to do that show a very big difference between objects we classify as planets versus dwarf planets. We've just not really come to a consensus on which of those metrics we want to use and where that point is that would really separate out between a planet and a dwarf planet.
Great. All right, all good points. Let's move on to our next question, and that is, why isn't Pluto a planet anymore? Which I think we already kind of discussed somewhat about, what classifies something as a planet, but why specifically is Pluto not a planet? And do scientists hate Pluto? Like, is it not a planet just because scientists don't like it? What happened to it? Did they kick it out of the solar system? Todd, help us out with that one.
Well, I think that the basic idea was already covered. If I just share my screen again, these are the points that John just made with the three rules of what is a planet defined, back in 2006. So it's kind of interesting when you look at the definition. There's some other issues that Pluto has had over the years, since its discovery, that made it a little bit of an oddball, to say the least. And that is a couple things we can look at here. Let's see, where did my slide go? The size, for one, and this may be jumping into another potential question, though. The sizes are very small, as you can see from the continental U.S.
Yeah, so Todd, go ahead and share your screen so we can see that.
Is it not sharing? Oh, okay. I thought I was sharing. Sorry, my bad. Share. Okay, so it's sharing now?
Yeah, we can see it.
Okay, so this is the International Astronomical Union's official definition, as John outlined, that came out 14 years ago. All right, so the third rule, as we were just talking about, has the object cleared its neighborhood. And so this was the point of failure for Pluto to be included in this formal new definition of a planet. And so the definition didn't really exist before 2006, which seems kind of odd because astronomy is a really old science, right? So it's been around for a long time. And the original sort of loose definition of a planet was really anything that was observed in the sky to move relative to the fixed pattern of stars we call constellations, right? So we always know that there's like constellations, they're seasonal. We see certain constellations in the winter and some in the summer, but that pattern to our eyes never really changes. We don't see the motions that those things have because those stars are just so far away. But planets were seen as points of light that looked like brighter stars that were moving in certain directions during certain times, and they had a predictability to it. And that's where really the science of astronomy was born. But anything that moved relative to background stars was considered a planet. So if you go back to ancient history, the sun was a planet, the moon was a planet, right? And none of these things we would even consider today, or before this definition, modern times, would be considered a planet anymore. We know the sun is a star. We know the moon is a natural satellite of the Earth. And so we made these distinctions before. And it really came about that when another object that was discovered that was much like Pluto, that the problem started. But if I go to this particular slide here, This will let me do it. Nope. Jump around. Let me try to go to. Let me just jump down here. This one. Sorry. My mouse is a little jumpy. So the problems with Pluto with mass, if you look at the episodes here, the years where it was Planet X was even originally considered in 1848, there was estimates that there was something about 12 times the mass of the Earth out there. Now those were obviously bad calculations and error. And then around the turn of the century, the estimates came down to about 7 Earth masses. And then when Pluto was initially discovered in 1930, the estimates were originally something around 1 Earth mass. Well, that's considerably massive, right? Something, if you discover another planet, it's about the mass of the Earth, you would think that's got to be a planet. So there wasn't too much of a problem there, but you can see that there's a general trend that the mass estimates and measurements get smaller and smaller over time. 30 years later, in 1960, the estimates were down to 1/10 of the mass of the Earth. And in 1970s, it was down to 3/1000 the mass of the Earth. And then the real clincher here is in 1978, that's when the moon of Pluto was discovered, and that really put the hurt on for Pluto and its planet status, because now you're looking at something that is more like a binary planet, because the moon was so significantly significant in comparison to size and mass of Pluto itself, as well as getting the very first accurate measurement of mass. Because one real important thing in astronomy, when you're trying to determine the mass of something, you really have to have something orbiting it, or a satellite, like a man-made satellite going off and flying by it, and make the measurements of how the gravitational pull affects that satellite. And so this was when we really knew that the mass of Pluto was only about 2/1000 the mass of the Earth. And so I had this picture here where it looks like Pluto's kind of upset about this moon that's about half the size and perhaps mass of the planet itself, which is that doesn't exist in the solar system anywhere else either, that we know of, as far as planets are concerned. And this is before the flyby of the New Horizons spacecraft. And so this is looks like they basically just pasted an image of Europa, one of the moons of Jupiter.
Yeah.
And because this is not what Charon looks like. And so down here on the bottom left, I have one of the flyby images of Charon down here. But that's the significance of 1978. When it was discovered, it was just looking at different blobs. And so that's kind of what fooled people for many decades. It wasn't resolved to be 2 different objects. And so the optics weren't the viewing wasn't good enough to distinguish that. And when they did, they got very accurate measurements.
Yeah, so they saw these 2 objects almost appear as one, and then that had them confused with its mass and the size of this object, just because they couldn't resolve that it's actually 2 separate things. That's really interesting, and I think that we're going to hear a little bit more about that from Rachel a little later, but Rachel's going to go ahead and answer our next question. So our next question is, how big is the Kuiper belt? So I mentioned beyond Neptune, there's this belt called the Kuiper belt. It's like Viper, but with a K. And how big is it, and how did it get there? Rachel?
Okay, so the Kuiper belt is kind of similar to the asteroid belt. Can you see my image? Okay. So the Kuiper belt, you can see, is out beyond the orbit of Neptune, and it is more of a donut than a belt, really, because it's got, depth and width and height. It starts about 30 AUs, or which is an astronomical unit, out, and is about 20 to 25 AUs across on each end of the donut. So
as a reminder, an astronomical unit, or an AU, is about 93 million miles. So 50 times that. That's billions and billions of miles from our Earth.
Right. So because it's the average of the distance between Earth and the sun. So it's extremely vast. And so with it being roughly 30 AUs across on one end, it's huge just if you look at that. But that's just the main part of the Kuiper belt. Even further beyond the Kuiper belt is a region we call the scatter disk. And some scientists consider the scatter disk to be a part of the Kuiper belt. And if you consider that part of the Kuiper belt, then it can extend up to about 1,000 AUs out from our solar system. So depending on how you define the Kuiper belt, the size of the Kuiper belt kind of changes if you include the scatter disk or not.
So that would be trillions of miles away from the sun.
Yeah.
That's far.
So huge, yeah. So a lot of people also tend to ask where the Kuiper belt came from. And we think that a lot of these Kuiper belt objects are leftovers, like icy leftovers from the formation of our solar system. And due to the gravity of Neptune and possibly some other bodies, they weren't quite able to combine into a planet. Plus, you also have the fact, like we just addressed, of how large of an area we're talking about. And I like this picture because unlike most of the pictures that you look for online, they have, materials everywhere, like in the asteroid field. But these objects are actually pretty far apart. So we have to draw pictures like this where they look like they're a lot more clustered. Otherwise, you just don't really notice. If we drew them to scale, you really wouldn't see them. So, but I like this one because they're a little bit more sparsely populated. It makes it a little easier to understand.
Absolutely. Thanks, Rachel. All right. So the next question, I'm actually going to take this one. How long does it take for the light reflected by Pluto to arrive to Earth? So if we make an observation of Pluto, how old is that light? Because it does take time for light to travel from place to place in our solar system and our universe. For instance, it takes light 8 minutes to reach Earth from the sun. All the sunlight that we're seeing in the daytime sky is about 8 minutes old. But what about Pluto? Pluto's really far away, right? So as a reminder, here's our solar system model again. We have all the planets here, the sun at the center. That kind of blends in with the other stars at this distance that we're viewing the solar system from here, because this is more or less the scale. So Rachel just showed a model of the solar system where things were in a little bit larger than what you actually would see if you were out in space looking back at the sun at this distance. But this is pretty much the scale here. And so we can see the orbit line for Pluto out beyond Neptune's orbit line here. And Pluto is sometimes closer to the sun, sometimes farther away. It has an elliptical orbit around the sun. So this makes it be between 30 to 50 times the Earth-Sun distance, so that astronomical unit that we mentioned before. And that's an average of about 3.6 billion miles, so billions of miles from the sun. And since it's that far away, it takes 4 to 7 hours for light to reach us from Pluto. 4 to 7 hours. Light from the sun, remember, to reach Earth takes about 8 minutes. Light from Pluto, reflected light from Pluto, takes about 4 to 7 hours to reach us here on Earth. And at that distance, so if you're on Pluto looking out at the sky, the sun appears to be about 1,600 times dimmer than it does here on Earth. 1,600 times. So it kind of blends in with all the stars in the sky at that point. Our solar system is huge and it takes many years to explore it. And so I think we're going to skip ahead a little bit and hear from Rachel again on if we have a spacecraft visiting, because it does take a long time to explore these objects. I know Todd mentioned that there was this craft that did go and explore Pluto up close, but Rachel, can you help us out and help us understand more about that spacecraft? Jumping ahead again.
Yes, I can.
Great.
One of the questions was, have we ever visited Pluto? People, no. Robots, yes. So we sent out the New Horizons spacecraft fairly recently. And so thanks to it, we have beautiful images of Pluto that we didn't have when I was growing up. When I was growing up, Pluto looked more like, yeah, this pretty much. So this was my first image of Pluto, and eventually it got a little better. We used Hubble to get some images, but they just weren't the best. So we sent New Horizons. We launched it in 2006, and we used Jupiter as a gravity assist, and it reached Pluto roughly in 2015. And was able to start getting pictures of Pluto in much, much better detail than we'd ever seen before. And as it got closer and closer, the images got more detailed as it went. So we can see, there we go. So here's a picture from New Horizons. And then there's one that's a little bit more detailed because it got a little closer. It was later on in that, I think the same year. But you can see that compared to the 1996 image is just phenomenal. The detail is great. And one of the cool features that a lot of people noticed right away was this kind of heart shape. So a lot of cartoons and everything that you see with Pluto now has a little heart on what it looks like on its cheek. So there's some fascinating things, and there's even images that are much closer up than this. You can see the different details on the surface.
Yeah, I think we're going to look at some of those later, and maybe Todd has some pictures of that, or is going to explain a little bit more about that heart-shaped region on Pluto.
Oh, sure. Yeah, I've got a slide somewhere here. I think it's a zoom in of that area. Let me make sure I'm sharing my screen. Share. Okay. So this is the closest approach to Pluto. The resolution, which basically is how well you can see distances, the smallest distance separation between, say, surface features on Pluto, got to be somewhere on the order of 250 feet or 77 meters per pixel. So all these images are made up of little tiny individual pixels in the digital camera that's on board the spacecraft. And this tells you basically how much actual physical distance is between them. And so when this goes through its little flyby, and so now you can see the scale, 6 mile scale on the bottom right. You can see craters. We're getting into the area where this would be the area of that heart shape. Looks very frosted. I believe that the frosting there is frozen nitrogen. Mm-hmm. And kind of a interesting planar region, little mountainous regions, and you can see the almost like snow drifts.
That's
just quite amazing.
Yeah, we have better pictures of Pluto than we do of Uranus and Neptune, and this definitely highlights that, which I think is great because we sent New Horizons after the Voyager space probe visited Uranus and Neptune, so it's quite amazing. But what about other dwarf planets? Are there other dwarf planets out there? We already know yes, because I kind of introed them at the beginning of the talk here. But I think, Rachel, you're going to help us explore some of those other dwarf planets.
Okay. So we have right now 5 confirmed dwarf planets, and there's probably many more out there that we haven't either discovered or haven't confirmed as dwarf planets. But currently we have Pluto, Eris, Haumea, Makemake, no, it looks like Make, but it's Makemake, and Ceres. So Ceres is kind of interesting because it's the only one that's inside the inner solar system. The rest of these objects are located out in the Kuiper belt. So these ones are pretty fascinating. Haumea actually has a ring around it and is kind of egg-shaped because it spins so fast. It rotates like, I think once every 4 hours or something like that, roughly. And then, so beyond Neptune, there are also, there we go, many other objects. Some of these may end up being classified as dwarf planets in the future. And you can see some dwarf planets have moons of their own. So it's pretty fascinating. And some of these are still in the process of getting named. So you'll see they just kind of a designation. And so some of them are pretty fascinating. Like you've got Orcus over here, which is a pretty fun name to say.
I think it's amazing that Pluto has 5 moons. We have 1, and Pluto's smaller than our moon.
I know.
And it
5
has
sounds
5.
like it's doing a really, it's trying really hard to clear out its area.
It's trying so hard to be a planet.
It's just clearing it out the area by gathering them up and keeping them.
Yeah, I just want some company out there in the Kuiper belt.
Yeah.
All right. But
oh, sorry.
Oh, I'm sorry. Did you have more to add?
Just a little. If you want to like kind of help teach your kids about the dwarf planets, there's actually a really fun and catchy song on YouTube called the Dwarf Planet Song by a channel called Hopscotch. And it gives you a lot of really good information about each one of the 5 dwarf planets out there, and it's very cute.
It is very good, and I recommend it for adults too. You don't have to have kids to enjoy it.
All ages.
Kids of all ages, yeah. All right, so what about anything past Pluto besides dwarf planets? Like, could there be another planet out there? And we actually have a program at the planetarium that we play at the planetarium from the Adler Planetarium called Planet 9 that does an amazing job about outlining the search for a possible 9th planet in our solar system, a true 9th planet. But what do we know about that? I think, John, you're going to help us out with that one.
Yeah, and the simple answer to the question of whether there is another planet out beyond Pluto is maybe. And back in 2015, Caltech scientists were studying some objects out in the Kuiper Belt region, out beyond Pluto, and they discovered that a few of these objects were moving in a strange way. They weren't following a predicted orbit as you would expect around the sun, and that something must be influencing their motion. So they did some calculations, and they found that they could explain those perturbations, those small unexpected changes in their motion, if there was another Neptune-sized planet, so about 10 times the mass of the sun, that was orbiting way out past Pluto. And it doesn't have an official name yet that I'm aware of, but it would be so far out, it's about 20 times farther from the sun than Neptune is. So this would be a large gas giant-like planet that would be really far out there in the solar system. When Dana showed that scale of the solar system earlier, and even how far out you get to the Kuiper Belt, you're looking where you sort of get to that edge of that Kuiper Belt. It's about 20 times farther out than that. But it would begin to explain some of these strange things that we see. However, scientists haven't been able to come to an agreement on the calculations because when you start looking that far out, the level of detail and precision that you can make your measurements isn't quite as good. And so scientists are continuing to follow up and try to get better data, which is how we sort of proceed in the scientific method. We make a prediction, and then we try to take measurements to confirm if our prediction is correct. And so we're kind of in that stage of this process, trying to figure out if this thing that we think might be out there, in fact, is there, and then confirming that it is also a planet. And also just of note, because it is so far out, and we have not been able to resolve it with a telescope. So even if it's there at all, it's not something we've been actually able to even see to confirm its presence.
All right, so it's really exciting that there's some things that we don't know about yet in our even in our solar system, and that's what science is all about, right? Trying to figure out new things about the world around us. So going back to Pluto here, one of the questions that was asked to another planetarian, so again, a planetarian is someone who works in a planetarium, is Pluto called a dwarf planet because it has a lot of gold in it? And Rachel, I think you're going to help us with that one.
Yeah. Here we go. All right, is the screen showing okay?
Yeah.
Okay, good. So no, Pluto's not made of gold, and I'm guessing that was a reference to Snow White and the Seven Dwarfs. Maybe that's kind of along the lines of where they were thinking. But Pluto was reclassified as a dwarf planet because, as we covered earlier, it just doesn't quite have enough mass to clear out its neighborhood of other objects. And Pluto's actually made of rock and ices, and we've now kind of know that it's more like methane ice, nitrogen ice, and we suspect even some water ice. So this is an image from New Horizons. It's been colorized based upon the different types of ice that they suspect. If I remember right, do you guys remember if the brownish red, I think that's the methane ice? I'm not sure. I can't really remember for sure. Maybe the blue is the methane.
Yeah, I'm not sure either, but definitely the colors there are representing chemical abundance. So representing that there's other things there besides maybe just rock.
Right. So it's not a true color image, but it helps us to understand and study more of what Pluto actually looks like. And one of the coolest facts I've learned about Pluto recently is that it actually has an atmosphere, which I didn't know that before. It's a hazy atmosphere, and we think it's kind of thin, but it does have an atmosphere, which just blew my mind.
Yeah, and I think I'm going to talk about that in the next question here. So the next question is, why aren't there many craters on some of Pluto? Then also, does it have an atmosphere? So we just heard that it does. And what are some things we're still trying to figure out about Pluto? So that's a lot of questions, but they are all kind of tied to one another. So let's try to figure out some of those answers. So going back to our solar system model here, we know that at its closest approach to the sun, Pluto can get to about 90 or minus 370 degrees Fahrenheit. So Pluto's really far from the sun, where we get our heat and our warmth from. So it's really cold out by Pluto. It's negative 370 degrees Fahrenheit. But then also Pluto can get even farther from the sun and get even colder at negative 390 degrees Fahrenheit. So this temperature difference of just 20 degrees at this far point can create seasons. And Pluto takes a really long time to orbit the sun one time. It takes about 248 years to go around the sun once in its orbit. And so each season on Pluto can last about 62 years. So a season on Pluto lasts about 62 years. It's really long compared to our seasons. So these extreme seasons can actually change some things on Pluto, just like the seasons change things on our planet Earth. And so here's a photo here that shows the size of Pluto compared to our Earth, our moon. And you can see that Pluto is smaller than our moon. It's about 1,400 miles wide. And its composition, as Rachel mentioned before, it has a surface of nitrogen and methane ices. It's mostly nitrogen ices. It might have a rocky core. And they thought maybe that there's water ice beneath this nitrogen and methane ice cover, but they're actually thinking that might be liquid. So there's some signatures on Pluto that show that there's probably not frozen water underneath it, but liquid water. It could have an internal ocean. So that's kind of exciting because where we see liquid water, there might be life there. But because it's made of these ices, and since it does get heated during the different seasons on Pluto, we can see that there are differences in the features on this dwarf planet, maybe because of that temperature change, or maybe because of other processes happening deep down below Pluto's surface. But we can see here in this picture that there's some smooth areas. So this is the heart-shaped region that we flew over with Todd, and it just does not have any craters on it. And then there's some other areas that you can definitely see craters. There's differences in the surface features here. And we found that Pluto is really kind of full of these surprises. And why is this a surprise? So why is it surprising that there's some smooth areas and some cratered areas? We see that on Earth. Why is it so weird to see it on Pluto? Well, on Earth, we have geological processes like volcanoes, water, and wind erosion. And we didn't really expect to see any of that on Pluto. So something must be happening on Pluto to erase craters over time, because every object in our solar system has gotten hit by other objects. There's going to be craters on the surface unless something erases it. So the smooth area, it's called Tombaugh Regio, named from the person who discovered Pluto, Clyde Tombaugh. So Tombaugh Regio, that heart region that we saw earlier and that you can see here in this picture, the smooth area, it doesn't have any craters, maybe because there's some ices rising from Pluto's interior that could erase the craters over time, maybe because of the decay of natural radioactive elements in a rocky core that generates some heat, maybe because of the seasons that it's experiencing. But if that was the case, then other parts of Pluto here would see some changes, some erasing of craters over time too. So most scientists think that it's something happening deep within Pluto's interior to erase these craters. And just to point out some of the features here, so from afar, so that smooth area again is Tombaugh Regio, and again, scientists haven't found a single crater on it, and that means that it's a younger surface. Something's erasing those craters over time, and so it can only be tens of millions years old. But then there's other features on Pluto as well. It's a very dynamic place. And so scientists are still trying to find out what exactly is causing all of these differences in the features on Pluto. And as Rachel mentioned, Pluto does have an atmosphere. This is another view of it. And if you look closely, you can maybe see that there is a star right here. And by looking at the light of this far distant star, as that light passes through Pluto's atmosphere, we can get information about the atmosphere around Pluto. It's kind of like a mini eclipse here that you're seeing. And as Pluto moved in front of the star, the atmosphere affected the light that passed through it. It changed how bright the star appeared. And by measuring that change in light, a lot can be figured out about the atmosphere, including what's in it, how much stuff there is, how thick is it basically, and how it's changing over time. And they did see that it does change with the seasons. So when Pluto is maybe warmer, the ices on the surface of Pluto melt and form this atmosphere around it. And the color here is actually pretty accurate. We have some blue that we see here, and it's blue for the same reason Earth's is. Earth's atmosphere is blue. It's scattering of light by the nitrogen molecules in Pluto's atmosphere. Pluto's atmosphere is mostly nitrogen, which would make sense because it has a lot of nitrogen ices on the surface of it. So if that nitrogen ice heats up, it becomes gas, it would then form a nitrogen atmosphere. Our atmosphere on Earth is about 80% nitrogen. So we have the nitrogen molecules in our atmosphere scattering light from the sun, making our atmosphere appear blue, and Pluto has the same sort of science going on there too. All right, so We have some questions coming in on the chat here that we can see if we can answer. Let me go ahead and stop sharing my screen here. Turn it over to the panelists here. And then we have a couple more questions on our list. But I think some of them I'm going to save for the end here. So let's go with the live questions. And if you do have a question at this point and want to ask it, put it in the chat. We'll get to it. So question from barber lady, Angela. Do we know the elevations of some of the features on Pluto? Does anyone want to take that?
Ooh, that's a tough one. I don't know any numbers with those elevations, but it would be interesting to know, like, what's the deepest crater. If you go back to that picture you had that you were showing, you can kind of get a good idea of why, like, that Tombaugh region is so smooth. You can see one of the craters looks like it's just perfectly filled in. It's at the bottom right of that picture. It looks like it's just completely filled in with that frost. Yeah, right there.
Yeah, there's like maybe some glaciers moving around. Yeah.
Yeah, and that's really, you know, and then the rest of it, some of it, you know, is there sort of, are they like mountainous, hilly regions, or is it rubble piles like you see on comets that may have accumulated from just those few moons that are around it? That's another question.
Yeah,
but,
here's another
know.
picture here of a close-up region of Pluto. And so you can see mountains. There is a lot of elevation. There's hills down in the lower right here, but then there's also mountains there too. And they reach thousands of feet above the surface of Pluto.
Wow.
Yeah.
Yeah, and it just, you know, how are those changing over time, if at all? Making Pluto geologically active could be another argument for planethood. So we got to go back.
Well,
see, the problem with New Horizons was it was just a flyby. It wasn't an orbit, right?
Mm-hmm. Yeah, it was a flyby mission, and that's usually where scientists start. They do a kind of a scouting mission to explore objects in our solar system, and so they wanted to fly by Pluto, and maybe one day we'll send a spacecraft to orbit it. All right, we got to thank you for that answer. So you're very welcome. If there are any other questions, put them in the chat. If you're just joining us, we have Rachel Williamson, our planetarium show specialist from Ball State's Planetarium. We have John Millis, department chair for the Department of Physics and Astronomy, which the planetarium is a part of here at Ball State. And then Todd Vaccaro too. And I am Dana Thompson, director of the planetarium. While we're waiting on any other questions coming through, I wanted to kind of end with a really big one. And that is, do you think Pluto should be a planet? So I'm going to go in order here with Rachel first.
Do I personally think it should be a planet? No, because it just doesn't fit all of the criteria, as well as it's smaller than a lot of moons out there. I mean, granted, there's some, like Jupiter's got some huge moons, but still, it just, yeah, I think it fits better the classification of dwarf planet. Plus, it's a special dwarf planet because it's the largest dwarf planet, so it's still special.
It is still special. It's still there. It's even more special than I think scientists thought it was, based on the images we got from New Horizons. Todd, what about you? Do you think Pluto should be a planet?
Well, I mean, I have kind of a deeper connection with Pluto in a sense that when I was sort of in the third grade, I read a short story about Clyde Tombaugh, and that's what really got me interested in astronomy as a kid. And discovering Pluto has always been sort of at the core of my passion for astronomy. And when they were coming up with the definitions, unfortunately, I was not part of the IAU in 2006. It would be a year later that I would join, so I didn't get to vote. But I probably would have voted to keep it a planet. I think it's important that there be definitions, but in this case, I think if it's massive enough to be round enough and it has several moons, I think it should be considered a planet. And I don't know if it was more of a, I know it's different. I mean, if you look at the density of Pluto, it doesn't even fit with any of the other planets. You're either sort of a rocky planet like Earth at about 5 grams per cubic centimeter, or you're a gas giant that you're barely more dense than water on average, like Jupiter and Saturn. Well, Saturn's actually less dense than water, but you know, Pluto is sort of in between. And it doesn't even fit a comet's average density. So it is kind of a new thing. But I think it's big enough and massive enough to be round. I have no trouble calling Eris a planet and Ceres a planet, but that's just me.
Yeah, I agree. Like if you call Pluto a planet, you definitely have to call Eris a planet.
Oh, sure.
Yeah.
Yeah, and then it gets a little complicated, right? But before we get to John's answer, I'm going to show you how complicated some of this is. We have all of these different categories for objects in our solar system. As you can see in this diagram here, we have planet, we have dwarf planet, minor planets, trans-Neptunian objects. So that would be like objects in the Kuiper belt and beyond. And then we have satellites, so our moons. And then we have all these other things. And there's a lot of overlap between almost everything here. I think everything here, there's overlap except for planets. So perhaps maybe we need to think about some overlap between planet and these other things considering. Well, I mean, there's no overlap between satellites and dwarf planets or small solar system bodies and satellites. So, but it does get complicated, as you can see. All right, John.
Pluto does get to sort of survive with the Plutoids designation, right? As a unique dwarf planet.
Unique aspect of the dwarf planet. And we have minor planet too. And we do want to point out that there is still planet in these names. So that can be maybe a middle ground for some people. All right, John, what do you think? Should Pluto be a planet?
Well, actually, if you want to leave that up, that's actually a really good segue into what I was going to say about it, which is really that definitions and classifications are important. And particularly as we are now at a point where we are beginning to look beyond our own solar system. We're finding, studying, and classifying planets around other stars and thinking about what it means for an object to be a planet, a moon, a dwarf planet, a other solar system body like a comet or an asteroid is really important because our universe, in terms of our understanding of the word planet, is getting bigger. And so we need to have definitions. And I think this diagram is a good example as to why that is, because right now it's still messy and I think we're still sorting it out. One of the things we discussed when we met earlier this week to talk about this was the fact that we still don't even have a definition for what a moon is, right? That's still something scientists are debating and talking about and thinking about. And so as we look at diagrams like this, we see that it's messy, it's complicated. And as we begin to look beyond our own solar system, we need to think about how can we simplify things and come to a common understanding for what objects in the universe are, so that when a scientist from Ball State finds a planet or an object around another star, that there isn't any ambiguity as to how to classify it. And so should Pluto be a planet? Well, currently looking at this diagram, that's a really messy question to ask, right? Because there's still quite a bit of ambiguity and there's the historical perspective that we also have to consider. But I think my answer would be that no, I don't think Pluto should be a planet. And I think it's because as we begin to separate out the objects and really try to define what makes certain objects fall into certain classifications, it seems to me that Pluto falls into a different classification than the other 8 objects orbiting our sun that we call planets. And so for that reason alone, and because of the need for a consistent definition as our understanding of the planets and dwarf planets expands to other solar systems, I think we need to find a consistent way of doing that. And that seems to be over that line for what I would call a planet.
I think those are really good points, and I would agree. And I think that it's okay that science is changing, because we didn't know that there are those other objects by Pluto. We didn't know its size for a while. So having better observations is really helping us better map out and categorize objects in our solar system. So when people get really upset about Pluto not being a planet, I try to remind them that Ceres was discovered about 100 years beforehand, and it was originally called a planet, but then we found thousands of objects by Ceres. And so if we were calling Ceres a planet, we could probably call those other thousands of objects planets too. And it gets really complicated and confusing, especially when you're trying to test people on the planets in the solar system. So they then called Ceres an asteroid, and now it's called a dwarf planet as well. But so if you were to get upset about Pluto not being a planet, then yeah, like Rachel said earlier, then we have to get upset about Ceres not being a planet. We have to get upset about Eris and Haumea and Makemake, and that's a lot of things to be upset about. So let's just maybe call it something different.
I don't know why people really I've always thought or look at it as a demotion. It's not really a demotion. It's just a reclassification.
Exactly. Yeah.
And if you want to actually advocate for one of these objects, you could advocate for Pluto's moon, Charon. And Charon is actually I think it's about half the size of Pluto, but it's massive enough that as Pluto and Charon orbit each other, they actually behave more like a binary dwarf planet system than what we normally think of as a dwarf planet and a moon. So if you wanted to advocate for one of these objects, Charon is ripe for the picking to be classified as a dwarf planet itself in conjunction with Pluto. So just another interesting example to throw onto the pile.
Yeah, and as a reminder, Charon, or I've heard it Charon, so like share on, based on I think the kind of the person who was who was kind of named for in a way, but is a moon of Pluto. Yeah, thank you, Todd.
So yeah, there's
go ahead.
This is as New Horizons was getting closer and closer, so it still looks like a bunch of pixels, blobs, but that's Pluto orbiting the common center of mass, which is a little X there, and then there's Charon. So the center of mass of the system just between these two objects is outside of Pluto, which is also a weird sort of thing when you think about planets. You know, the Earth-Moon system, the center of mass between the Earth and the Moon is inside the Earth. So the Earth has a little bit of wobble to it when it orbits, or the Moon, and the Moon orbits the Earth. But this one's clearly got sort of a binary characteristic to it, and so it probably should be classified as a binary dwarf planet.
And they're both tidally locked to each other. Like our moon is tidally locked to us, meaning we always see the same side of the moon, but the moon doesn't always see the same side of Earth. Charon and Pluto are both tidally locked, so they always see the same side with each other, which is very unique.
That raises an interesting point, because that tidal locking, that's the synchronicity of both of them, should actually mean that there's not much tidal, if any, warming of the interior of either one of the objects. So the warming of Pluto to get liquid water would have to be, I guess, a radioactive process.
Yeah, so I think radioactivity, or perhaps even heat still from a collision. I think maybe those moons, the 5 moons that Pluto has, came about from a collision early on. And so maybe there's still some heat present from that collision. Yeah.
Cool.
All right. Well, I don't see any other questions coming through the chat, but if someone's watching this later and has a question about Pluto, dwarf planets, the Kuiper belt, or anything else about our solar system, you can go ahead and put it in the comments area, and we'll go ahead and answer it later when we can. But thank you, Rachel, Todd, and John, for joining us in this panel and exploring Pluto with us.
Yes.
Thanks for having me.
Thanks
Great
for
to be
having
here.
us.
All right. So just a heads up for everyone for our Your Universe series. Next week, we are exploring a lot of different things, but a part of that week, we're going to be exploring exoplanets. And we're going to have a Ball State grad student, Daniel Broussard, helping us out there, explaining some things that he's been doing in his research, as well as some of the discoveries being made about planets beyond our sun and our solar system. So join us for that next Friday at 11 o'clock, same time. And thanks everyone for watching. Have a great rest of your day and a wonderful weekend.